Alright, I have exactly one thing left to do. If placed, whatever. If placed equals data number of flag, pretty much, for int I equals 0, I is less than grid span, again, I plus plus, if data squares sub I and flagged, or, and I do have to do this, I remember this gets me all the time, or data squares sub I and checked. Oh wait, I want to do this. So basically we want the opposite of this. So if it's neither flagged nor checked, then break out. If it's not flagged or it's not checked, break out of the for loop. Otherwise, or no, we're gonna return 0. So if you find any square that is not flagged or not checked, just return. We're done. Otherwise, if we get all the way out of that win condition, for now, trace log debug right, you win somehow. So I am going to map hack. I'm going to cheat a little bit right here. And I'm going to draw all of my numbers just to test it. So easy. Alright, so I'm going to click on all the 0 ones are bombs, I think, yeah? Okay. Oh, okay. Oh, that's tricky. That's not helpful. Can I just safely click on it? No, I can't. Yeah, you can't. I can't even cheat at this. That's crazy. Alright. I might as well put that back. I kind of just want to cheat, but I don't know how. But anyway, I have this mysterious win condition that happens. So what happens is, if your number of placed flags is equal to the number of flags, what we're going to do is loop through everything. If the square at this location is not flagged, or it is, and if it's not flagged and it's not checked, return 0. You did not win, continue everything. And then we're going to do data dot game started equals 0. That's what I'm going to plan to do here. Yeah, okay. Okay. So I can't reach the win condition. I'll have to think of I have to actually hack the game. I'll have to think of a way to cheat, and then once I do, I can confirm that that works. But for now, this game is theoretically feature complete. I've increased the font size so that it just kind of occurred to me that I'm on a 2K monitor, but I'm also like, foot away from it. I can see everything very well. but I don't know how that's going to come out in video. In CLion, anyway, if you type anything at all right here for your struct, you don't make it anonymous, you can hover over it and it'll tell you the size and the alignment. And I briefly went over that a while ago, but we'll refresh a little bit. Alignment is the size of the largest primitive, I believe. So if I make another struct that's 60, but its largest thing inside of it is 8, and so on and so forth recursively, then it will be aligned to its largest, we'll call it primitive. So in my case, it's a pointer. A pointer is 8 bytes. A double is also 8 bytes. A long is also 8 bytes. So this is 48. It goes 8 and then 4, but it's aligned. Usually, if you start getting, let's make a double. Let's make this a double, just for fun. Okay, this is 8. This is 8. This is 8. This is 4. This is 4. If I move this here, we go to 56. So we go 8, and then we go 4, but there's plus 4 padding because we're aligned by 8 now. So 8 and then 4, and then it has to have 4 bytes of padding to fit into this alignment. It does seem to even itself out below though, so that's interesting. I did not know that it would do that. Anyway, we're going to talk about it for real though. This right here is 48. I reckon I could probably have that. And I'm going to show how I would do that. And we'll talk a little bit about why you would do that too. So my first instinct is take all of the smallest things and put them at the bottom. Put these down here. Number flag. Grid row column. Okay. So this is a benefit that we have because we determined that the largest our size is going to be 25 by 25, and we're representing them as row call times row call, right? So row call times row call, grid span, row call. So we've determined that 25 is the largest size. So let's pull up a decimal to binary calculator real quick. I'm going to say 25. It looks like we need 5 bytes, or 5 bits to represent 25. So I'm going to bring this over here. Now, I just want to make something very clear to you. You do not have to do this. You do not have to program like this. I'm doing this because I'm waiting for my RAM to heat up a board, and I find this to be interesting. But you absolutely do not need to do this. So don't ever think that you do. So I'm also going to move this down here. I'm going to do something interesting. I'm going to do this. I'm going to say this is a size 5. This is a bit field, this thing. And I'm going to say this is 1 because it only has 2 states. Technically, it does not have 2 states. It has 3 states. This one's a little difficult. So what we could probably do is we'll have to revisit that. Alright, you win today is game over. You go up there. Game started, that's a true or false. That is 1 bit of information. We don't need any more than that. Transition grace, 0 or 1, that's 1 bit. We don't need any more than that. Window height, I don't know how big that'll get. But since we already have all of our stuff established, we don't have to guess. We can actually just check. So padding is 20. 20 times 2 plus roll call, like we said, at max is 25. Times grid spacing was 20. What did I say it was? 20. Okay. Will it do the math for me? Oh, well, that's dumb. 540. That sounds about right to me. So let's say 540. 540. 10 digits. 10. Come on up here. Window. Height, I think that was. Let's say that this is 10. Move that up. Window width, 540 plus 200. I broke it. Sorry. So that's 7. That's 740. Also 10 digits. We walked away with that one. Okay. So let's keep track. 10, 20, 25, 26, 27. So we almost have a whole integer. Flags placed. I think the maximum number of flags placed was 125 when we need 7 digits. That'll make us go up to 34. Flags placed. 34. Or, sorry. 7. So this will put us at 34. Okay. Is game over? So I have to fix this. I have to change the behavior of the program in order to get this, but I could get this down to 1 bit. Number of flag. Same thing as flags placed. 7. Right? And elapsed is a float. Ah, you know what I could do? 2 bits. So 34 is now 36 bits. And now we're at so we're at 43 bits. Now let's take a look. 24. I was right. I halved it. Now how do I do that? And then we can fill out the rest with instance. 24. Okay, so this will be my padding. Right? Elapsed has to stay that way. And then probably get rid of all these comments. As far as I'm aware, the fields do not need to be in any particular order. And I don't know that it's even beneficial to put them in order. But can't hurt, I guess. But yeah, I have it. How did that happen? So these are 4 or 8 and then 4 bytes. And this is 10 bits, 20 bits, 27 bits, 34 bits, 36, 37, 38, 43 bits. So 64 is 43. I actually have 20. Alright. Yeah, I don't know how to do math. I have 21 bits free. So I can actually store more information in here now and still take up less space than what was there before, because it was 48. Now how does this happen? Why would I do this? And all that stuff. First of all, before I answer that, where is Fortran game started is game over. Where is game over? Data is game over. I'm gonna set this to 2. If data is game over, return. Not data is game over. Let's see if that still works. Almost. I did something wrong. Let's try that again. Whew! That's fun. Alright. Data is game over is -2. Oh! Can I do that? I'm gonna just leave this as -1. Width is greater than or equal to 0. Line 6. Window.c. Oh. Alright, so good. We have some bits to spare, so we can fix that, but that was an interesting one. I haven't seen that bug before. 16 bits. So that takes away 12. Minus 12. Should have 9 left. I'm just doing this for records keeping. You don't actually have to do that. Still at 24. Still here, still selling fake doors. Game's still working. Is game over? Is -1. Game started is -1 also. Okay. So, I forgot one more important thing. Instead of these ints right here, we're just going to type unsigned and then stop. That's it. Unsigned what? They're just unsigned. They don't have a sign. Something else is going to break. I gotta go fix that real quick. Equals 2. The reason was that they had a sign bit. Restart. And as you can see here, is game over is equal to 2. Scroll on down to here. Equals 2. I forgot to switch that to. Hard. Bam. Bam. Game over. Restart. Okay. Take a look here. Is game over is 2. Game started is 1. Everything's going according to plan, dog. Game over. Restart. Game over. Restart. Bam. That was insanely lucky. I can switch my game modes. Everything works fine. Easy. Medium. This one. Restart. Bam. But yeah. All that, it still works. And I cut my size in half. So I could probably pop this off. I don't need it. I'm going to keep it there just for my own records. But what did I just do? So I just determined that window width did not need to be any bigger than 16 digits long. how many is 16 digits long? 16 digits can represent up to 65535. Problem that I was having was not anything other than it was unsigned. So this was split in half, and I only had 10 digits. So 10 digits is, what did I say it was? I was like doing the exact calculation of it. So I said, oh yeah, we don't need more than 5 or 700 of this. I think I said 720. So I don't need more than 10. The only problem is this 10th bit was a signed bit, so it was giving the window a negative number for its size. So that's why it was freaking out. So I didn't actually have to do that. I can put these back to 10 and recompile. Now that they're unsigned, we shouldn't have any issues. Great, everything looks fine. Damn, little pony. I guess if you hit restart by yourself, you can fill the game. Nice little bug. But yeah, so it turns out I didn't actually need that. I can add my 12 back to this, which is 21. I have 21 bits left for storage. I don't know if that excites anyone as much as it excites me, but look at all of this data that I just compressed down from 48 bytes to 24 bytes. And I could get even more in there. That's crazy. The only thing I regret is that I don't know how to store, because this is 4 bytes. I can't fit 32 into there. I start pulling away from other stuff, but I don't want to do that. So yeah, that's a fun thing that you can do. This is, now let's talk about it. I said I would. Let's talk about when you would do this and when you would not do it. When do you not do this? You do not do this where I just did this. You do not do this here. There's absolutely no reason to do that. Why? Because this is not really accessed every frame. And it is, but it's not like, how do I say this? One of these is accessed every frame. Exactly one is accessed every frame. If you have game objects that are like, you have like 32,000 of them, you can see how 24 times 32,000 might add up to some astronomically large number. It might make sense to do that there. If you're sending binary data over a network, if you're trying to make very small packets to network between things, it might make sense to do it there. If you're, what else would you even use that for? Saving binary data to a file, maybe? It might make sense to do it there. Does it always make sense in those circumstances? No, not even always. That's not a sure thing ever. This is just something you can do if you want to get super particular about how big everything is. And I've seen people who are millions of times smarter than I am say, don't bother with them at all. Do not even try to do them. You're just gonna hurt yourself. So take that with a grain of salt, but that's one thing that you could do should you be concerned about that. Another thing, embedded, like if you were to do like embedded stuff, I'm sure that this kind of stuff, like counting the bits in memory, is very important when you've only got like a couple of kilobytes to work with. But like, yeah, man, it doesn't, this is not one of those things that you have to do. This doesn't make you a better C programmer. This is just one of those hundreds of millions of ways that you can kind of eke out just a little bit more performance. In fact, let's go back down here. I regret that I deleted it, but let's see what it looked like, because I was getting anywhere from 3,900 to like 4,800 frames per second, and it was varying. So I'm just going to... Shoot, I'm just going to take that. This D. Burst. This is going to be get FPS. Right there. And I'm just gonna do, come on, 10, 10, 15, and green. So remember, 3800, 40 something hundred. Let's take a look. And it's exactly the same. Nothing at all has changed. We have some things peaking down. I saw 5, but I also saw 2. In fact, we might even be averaging a little bit lower. There it goes. So if I do stuff like this, you start moving around. Come back and do insane. See that one? I just got to 1400. Like, these frames are all over the place, and that could be for a lot of reasons. It's because we have to share this memory with the operating system and every other program on it. Notice that my performance really didn't go anywhere. In fact, it might have gone down. Well, why is that? Truth be told, the implementations of bit fields are still a little bit elusive to me. I don't really understand them all too well, or not perfectly anyway. If I could recommend you one thing, read up about bit fields. Understand them, why you should, when you should, and if you should use them. And then learn about the downsides of them too, because I feel like that might be just as important to know. Why would you not use a bit field? Why doesn't everyone program exactly like that? Because it seems like a pretty good idea, you know? This should only be 1 bit. Give me 1 bit. But it's apparently a little more complicated than that. After I finished last night, after talking about how this is a way to do things, where you bit field stuff, I decided to look into why people don't do this more often, and I found something interesting. Now, I am actually using GCC, so this is particularly relevant to me, but let's take a look. This is from lwn.net. It's Linux something, I don't know what. Why don't you use bit fields? So here's a pretty compelling reason. So you see they've got one little bit field right there. Okay. They've got a U64 size, U64 reserved, struct. I don't know what this is, but it's a pointer to something. A lock, and then an unsigned integer of size 1. So this is a 1-bit integer. Nothing out of the ordinary so far, but let's move on. It turns out if it generates a 64-bit read, modify, write cycle that reads both lock and full, modifies full, and then writes both fields back to memory. So basically, it takes this is a 32-bit integer, probably, presumably. I don't know what the system looks like, but 32-bit, and it realized that it's only a 1, so it also grabs this spin lock, which probably is a 32-bit. So it grabs both of them, because this is only 1 bit. Makes a 64-bit copy of the 2 of them, modifies this bit, and then puts them both back. That's what it looks like it's doing. And it turns out that as this is being pulled, this is a spin lock, right? So that tells me it's a lock of some sort. It might have to do with multi-threading, if I understand that correctly. I'm not really sure what it's doing, because I'm not privy to it, but when I hear the word lock, I think thread. So what they're complaining about is sometimes it will get corrupted, because as you pull these two out, the lock will be modified by something else, and then when you put these back, you have unmodified it. So you basically unlock a lock by overwriting the lock, I guess. So that's an interesting thing to think about right here. So that is why we don't always use bit fields, I guess. So something to think about. Mine happens to be, greater than 32. But you know what I should do? Just to make sure, I'll do that. So this is 10, 20, and then 32. So this is now the size of one integer, and then this has some remaining stuff. That doesn't make sense, does it? Did I do this math right? 10, 20, 27, 32, right? And then 7, 9, 10, 11, 21. Oh, that doesn't make sense. Okay. So yeah, that's just a little appendix